Welcome to this first lecture on deep reinforcement learning by the Machine Learning and AI Academy. In a series of lectures, we will be describing different types of reinforcement learning algorithms, including both their derivations and implementations in PyTorch. We hope you find this lecture series useful, and please ask any questions you have in the comments below. So in this course, we will cover different types of reinforcement learning algorithms and mention some of their applications. As learning outcomes, we hope that you get the capability of understanding and deriving different reinforcement learning algorithms, as well as the capability of implementing state-of-the-art algorithms in PyTorch, in addition to the understanding of the applications of reinforcement learning and how that is useful to your specific problem domains. On the way, we will also provide you with the tricks necessary to make reinforcement learning algorithms useful and work well. On a high level, we will cover two different types of algorithms from reinforcement learning. We will be describing model-free types of algorithms, as well as model-based types of algorithms. In model-free algorithms, the agent that typically interacts with the environment does not assume any additional restrictions on the model of the environment that is under study. All it does is it interacts with that environment, gets some form of data like traces or trajectories from that environment, and then tries to learn an action selection rule in order to maximize its performance. The model-based setting, on the other hand, it tries to build a surrogate environment from the traces it had collected from the real-world environment. In that surrogate environment, it tries to find the best action selection rule in order to maximize its performance measure. It thus updates the action selection rule or policy. Then it uses that policy to sample again from the real environment and so forth. Clearly, doing model-based is much more sample efficient than doing model-free. So to illustrate this, if I am to plot a graph where on the x-axis I represent the number of episodes, so that's the number of traces or the number of times the agent interacted with the real-world environment versus the reward. And for now, you can think about the reward as some form of a performance measure, so the higher the better. And I try to plot this learning curve, which is reward versus episodes. You might see for a model-free algorithm a curve that looks like this. Of course, this is a made-up curve, but all I want you to see from this curve is the more interactions we have with the environment, the more the reward is. So the higher the episodes, the higher the reward, which means the agent is learning. Though successful, current model-free, state-of-the-art model-free reinforcement learning algorithms, they require millions, or maybe let's say hundreds of thousands of interactions to learn something useful. So this is all good, but when it comes to real-world applications beyond Atari games, this is really, really hard to apply. And that's where the model-based counterpart comes into play, where if I am to plot this learning curve for the model-based algorithms, I would see a reward that looks like this, where numbers here are in the tens or hundreds of episodes. So all this is good, and clearly model-based is more sample efficient than model-free. So why don't we use model-based all the time? Well, it turns out that model-based does not work really well yet in very high-dimensional environments, such as, for instance, Atari games or any environment which has a state representation in the order of thousands. And that's why you have a trade-off to consider here, where you try to be as efficient as you can, depending on the dimensionality of your problem. And there are algorithms which reside in between these two, which are like model-based, model-free type of algorithms that try to get the best of both worlds. We will be describing these different algorithms and implementing some of them together with the hope that you are able to understand when to apply the model-free setting and when to apply the model-based setting. So at this stage, you might be wondering, why do you even attempt to learn reinforcement learning? Well, it turns out that reinforcement learning is a useful tool that can be applied to a wide range of possible applications. Applications involving robotics, computer games, cooling systems, logistics, finance, self-driving cars, among others. In all these applications, you always have an agent, and that agent is trying to perform a sequence of actions in the environment which is uncertain and stochastic. So, what does that really mean? So imagine you have the car in a self-driving car scenario, and that car has to go from a place to another. So at every state on the road, the car takes an action that transitions it to a successor state. However, this transition itself is not deterministic in the sense that if the car had applied the same action again in that specific state, it might end up in a slightly different successor state. The reason for that can be, for example, random sensors or noisy sensors. The environment itself might be stochastic. So, for example, a pedestrian suddenly decided to pop up, and so forth. And now the goal of the car is to take a sequence of actions such that it maximizes some notion of performance. So, for example, in the car, it shouldn't crash, it should have a safe driving maneuver, etc., etc. So, in general, a lot of problems can be described as instances of reinforcement learning where we have an agent that is performing a sequence of actions in an environment which is uncertain and stochastic, with the goal of maximizing a notion of return. It is important to note that there's a temporal nature to this problem. So we're not only interested in one step action application, but we're interested in a sequence of action applications. And the reason of that, because there's a trade-off between immediate action and future action applications. And that's what makes the problem a little bit more difficult. Because now you cannot just be greedy in the sense of taking the best action at this time step, because it might hurt you after 10 time steps. So this is the trade-off that reinforcement learning has also to consider in order to attain a successful action selection rule. Right, so by now we have understood that in reinforcement learning, we have an agent that is performing, as we agreed, a sequence of actions in an environment that is typically stochastic and uncertain. So to depict this idea, I'm just giving an example here where I have a car, which is our agent, in an environment which is like the road. And let's say the car's goal is maybe to navigate the road, go from a place to another comfortably, safely, and without crashing. So here we need a couple of things to be able to define this problem. The first thing we need is we need a set of states. So, for example, the car starts here and applies some sort of action so that after 10 steps it reaches there. So we're going to use here in this example the x and y position of the car as the state description of that car in this environment. Actions can correspond to maybe, like go left, go right, or throttle, brake, and so forth. And these actions are going to dictate how the car moves from a place to another in this environment. So the way this car moves in this environment, dependent on the state it was in and the action it had applied, takes the car to a new state according to a model of the environment, which we call a transition model. In addition to that, we need some form of performance quantifier, which is what is denoted here by the reward. So the reward is going to tell the car you did well, so you get like a plus plus reward. So for example, if the car didn't crash, then it gets a plus plus reward. But if the car, for instance, does some unsafe move, we can give it a negative number. And then the goal is to reinforce the positive numbers or the good things that happened in these traces or trajectories the car has executed in the environment. So, in short, to define the problem, we need four components. The first component is a set of states or the space of states. So these are, for example, the XY position of the car. We need the space of actions. So that's like the action set that we are going to allow the car to execute. We need the reward function, which is going to tell me how good the car is performing. And we need the transition model. And that transition model is some form of a stochastic equation that dictates the change of the car's state conditioned on a previous state and an action that has been executed. There are different types of these states, actions, rewards, and transition models that we consider in reinforcement learning. So, for example, the set of states can be continuous, as is the case in this car experiment. So here we say that the state of the car is, for example, in R2. So we say that the car ST, state ST of the car, belongs to R2, which means simply that the car's state is a two-dimensional vector, each being continuous. So in other words, when I write a notion that looks like this, I really mean that this is a vector of two components, and each component here is a real number. States, however, can also be discrete, not only continuous. So if you consider a grid world experiment, here the agent can go from a cell to another cell dependent on the actions it had applied. And there we have a set of discrete states that the agent can belong to. And that is also possible to define in reinforcement learning. Similarly, the action space. So the action space AT here, for example, is, let's say, maybe we're going to have a steering, braking, and heading angle, let's say. So for instance, the action space is R3, which means again that the action is a three-component vector, each being a real number. The reward is typically a function that takes as an input a state and an action, and it gives me a real number. So we typically write that as, you have a reward function R that is going to take from you some state at time tst, some action at time tat, and that is going to be some real value, which is going to denote if this state and action that has been executed by the agent is a good or a bad action to apply in that state. So if you get a positive number, that's good. If you get a negative number, that's bad. So mathematically, what we can do is we can write this reward R to be a mapping or a function, really, from the state space cross the action space to the set of real numbers. So this is a state, this is an action space, and that is mapped to the real numbers, and this is what the reward function is supposed to be doing. When it comes to the transition model, this is a stochastic transition model, and the goal of this transition model is to dictate how the state evolves over time depending on the actions applied. So if it was deterministic, your transition model, let's call it F, for example, your transition model F would be some function that will give me, for example, a value of the state as t. So that's the F, the transition model, as a function of the previous state and the previous action that has been applied. As we said, however, this transition model is going to be stochastic. And that's why it's not going to look like a function f like this, but it has to look like a probability density, typically a conditional probability density, which we will write as st conditioned on st minus 1 and at minus 1. We will dive into this in the next slide, but all I want you to get is to define this problem of reinforcement learning. We need a set of states or a space of states, which is, as we said here, can be like R2 in this example. We need a set of actions, like we described here. We need a reward function, and we need a transition model, which is typically a conditional transition model. So for you to fully understand these, you need a primer on the probability and densities. So please check out the other lectures we have on our channel, where my colleague describes this notion of probability densities much clearer. What we're going to do next in these slides is going to give an example building on top of that. But please do check that lecture for you to fully comprehend the mathematics behind these transition models. Right, so what we would like to do now is we would like to understand these notions that we derived before much better by maybe giving some examples. But let's do that at a more abstract level. So rather than having the car agent interacting on a road environment, let us just say that we have an agent, and that agent is talking to some sort of an environment. The way it interacts with that environment is by applying some actions on that environment. The environment then responds by a state and a reward. Now this process repeats, right? So in this new state, the agent then takes some other action. And as you remember, we had this notion of sequential actions. So now given a new state, the agent takes another action, the environment responds by a new state and a reward, and so forth. So as we said before, we're going to need a couple of components to be able to define this problem. So the first thing we need is, we said we need a state space, right? So a state space where each state belongs to. And we're going to assume for now that the state space S, right, is some continuous state space. So it is belonging, so it's a subset of a d-dimensional space. What this notation means, it means that every vector, when we say ST belongs to this state space S, we simply mean that this ST is a d-dimensional real vector where each component is a real number and it has size d, and that real number can be just from minus infinity to plus infinity. We also said that we need an action space, as we described before. So our action space A, that's another d2-dimensional space. And when I say that AT belongs to A, I mean that AT is a d2-dimensional vector. Each component in that d2-dimensional vector is a real number that can be between minus infinity and plus infinity. So that's all good, but now we need a couple of additional components as we described before. So we needed, for example, as you remember, the reward function. And that's a function that is going to simply map, so R, we're going to call it, that's going to simply map from S cross A to the real numbers. So you can think about R as some form of like a box, right? So this is a box. It will take some ST, which is in this space S, right? So this ST is in this space S. And it's going to also take some action AT, right? And that action AT is in this space A. And on the output, it will produce some real number, right? So that is going to be just some real number that somehow quantifies the performance of our agent. Now, please notice that The reward function can also be stochastic in its own right, but we're not going to discuss that just yet. We're going to assume that the reward function is something that is given, right? And that reward function is just a map or a function that takes a state st and action at and gives me a real number. Now, what makes reinforcement learning hard is that typically this reward function is not known to the agent in a sense that the agent can exploit the reward function to learn something useful. The only thing the agent has is just a set of numbers of like +1 or -1 or zeros, and they are typically very sparse as well. So you get a reward function which is always 0 and then suddenly +1. And then from that, the agent has to learn how to apply a set of actions correctly in order to maximize that type of total reward that it would get. Another component we mentioned is the transition model, and that's what we're going to dig into a little bit deeper now. So the transition model, we said, it was a stochastic map, right? A stochastic map that takes from me some state and an action. It gives me some distribution or density over successor states. So the way we're gonna write this, as we said, is we're gonna say that my state at time step t+1 is conditioned on the state at time t and the action at time t. And now that means that given some state st, applying an action at, there is some form of a conditional density over st+1, which means that st+1 does not take the same value every time we apply the same st and the same at. So this map is kind of a stochastic map. To better understand this, right, like the simplest form of this map, we can say that, all right, we're going to have st+1, right, as we said before, to be some function of st and at, right? So that is like the dynamics, like it's just like, for example, in a Mario game, this function is some awkward function, which is hard to determine, but it's like a function where you have Mario here, then it says jump, then Mario jumps. So the next frame is Mario jumping. So that's st+1, and the function is what maps this Mario jump to the new frame of jumping. But in order to make this stochastic, we're gonna need to add some form of randomness into this equation. A very simple way to do this, and that's not typically very successful, but like just to understand, a very, very, very simple way to do this is we're gonna say, okay, I'm gonna add some noise epsilon to this equation, right? So what I'm saying is that the noise itself is random. So that is like a random number. For example, in Python, you can write that as np.random.normal or something. So that's like a random number. So that means that this guy, because this is a random number, every time this guy can take different values depending on the samples you get from that distribution, right? So we have some distribution. So we have, like, let's say for now it's some sort of a Gaussian distribution, let's say, right? And then every time you ask a sample, right, from that distribution, you can get a different value for this epsilon t, right? So that means that the idea here is that this, because it can take different values, it's in fact a random variable. So now we added to this deterministic equation some form of a random variable noise coming from some distribution. The way we write that this guy is coming from some distribution, we just denote it in this notation, which says that guy is sampled from some distribution, right? So which means that epsilon t is a random variable. It has some density or distribution. And every time you instantiate epsilon t, you observe a value of epsilon t, what happens is you sample from this distribution P. But now notice that because this is a random variable, right, that makes this also a random variable, which means now st plus 1 is not just one value that you will observe. Even if you had applied the same st and at to this function f, right? So even if the function f took the same st and at, due to the possibility of observing in the same st and at different epsilon t values because it's a random variable, then st plus 1 is also a random variable. So this makes this transition stochastic, right? Which in turn means that every time I observe st and at, I can observe a different value for epsilon t, which means I can observe a different st plus 1. So why would anybody care for this? I mean, there are a lot of reasons, but it turns out that most real-world problems are stochastic of this nature. So for example, if you are considering a car and now you have some sensors that measure the position of the car, these sensors are typically noisy, so you have to consider them stochastic and so forth. But now we know that we have a state space, right, which is just some vector, an action space, some other vector, a reward function that takes the state and the action and gives me a transition, and gives me, sorry, a real value. And we have a transition, which is typically stochastic, so we write it in this way. We say that st plus 1 is conditioned on st and at. And what we really mean by that is that this is sampled from some probability density, let's call it P transition or something, and that is a conditional form of density. So maybe I can illustrate this a little bit better by assuming, just like let's go through a simple derivation of like some linear equation. So we're going to say that, okay, imagine that my st plus 1, so my next state, let's say for now it is a one-dimensional vector. So that means that d is equal to 1 in this scenario. And let's say that, well, you know what, this is going to be like some equation which is ast plus but and plus some noise, as we said there, right? So the idea now is that we're saying that st plus 1 is a 1D vector that results from a linear transition where you have ast plus but, sorry, ut should be at here. So that's just the action. And we're going to add some noise to this process, right? So this is going to add some epsilon t, some noise to this process. Let's further assume that this noise epsilon t is Gaussian noise, which has a mean 0 and a variance sigma squared. So when I write an equation like this, I simply mean by it the bell curve. And that bell curve has a mean, which is the expectation of epsilon, and a variance, which is the variance of epsilon t. Now, with this, you can derive the fact that st plus 1, given st and at, is also going to be sampled from another Gaussian, okay? The mean of that Gaussian is going to be ast plus bat, and the noise is going to be sigma squared. Don't really worry where this came from. We'll derive this later in the lecture. But now this is interesting to understand. So what this is saying, right, is that if your noise was Gaussian, okay, then your successor state st plus 1, conditioned on st and at, will also be a Gaussian, and it has a mean around ast plus bat, and it has some sigma squared variance. So that means that anytime you are at the state st and you apply an action at, your successor state can be is Gaussian distributed with that mean and that variance. In other words, if you have a block that is like your transition model, so you can take here ST and you can take here AT, and that gives you ST plus 1. If you are to apply this ST and AT multiple times, you will trace on the output some form of a Gaussian with a mean. So you will trace on the output some form of a Gaussian that maybe looks like this. And the mean of that Gaussian is going to be AST plus BAT. And the variance of that Gaussian is going to be the same as the noise variance. Which means that with time, as you observe this over and over and over again, then the distribution of this guy is going to be Gaussian, with the mean being the kind of deterministic part of this equation, and there's some variance sigma squared. Now, what makes RL also hard is that the agent does not have access to this function f, because if it had, you can in fact exploit this function f, right? And then based on that, you can try to determine a very good behaving action selection rule in order to have good action selections to maximize your performance. If you think about optimal control is very, very related to this setting of reinforcement learning. But in optimal control, you typically assume that you know your transition model F. Here, we're going to assume that we have no clue about the transition model nor the cost function. That being said, there are forms of optimal control that also don't consider the transition model to be known, but we're not going to dive into these just yet. Right. So far we have understood what is an MDP. We understood what is a reward function, what is a transition model. And we understood that the generic goal is to find some sort of a policy or an action selection rule, right, that dictates a good behavior. So the remaining part that we need to describe before going forward is this action selection rule. So remember that at every time step t, right, our agent is executing an action AT, right? So we're going to have some action AT at every time step t executed by this agent. What we're going to say is we're going to say that that action A, that action AT, right, for it to be informative, it's going to be some function of a state ST. So in other words, you give me a state, then there's some function or some map, really, because AT can be d-dimensional, that will give me AT. Now, this function itself, right, can be also parameterized. So for example, you can have a neural network here, and we will dive into this in a second. But for now, we need to have some function that will pick the actions, and we're going to look for the best sort of function that picks the best actions to maximize performance. That's kind of the goal, right? So we need right? So we need the best. This we're going to call this function a policy, right? So we're going to need the best policy, which is like the action selection rule. We need the best policy. That's what we're going to do. So we're going to try to find the best policy. So here there are some notions to understand still. What do we mean by best, and what type of policy we're going to consider? Right. So now the idea is that this policy itself, we can ask the question now, right? If this policy itself has to be deterministic, right, or stochastic. In general, you can actually use any of these forms. So you can have also a deterministic policy, which is given a state ST, will give you the same action AT. But here's the trick. or here's what's hard. Because we don't know the transition dynamics of our environment, we don't know that, right? Remember, P that dictates the transition ST to ST plus 1 is not known to the agent. The agent is faced with a dilemma where it needs to explore versus exploit. In other words, the agent can now use the current policy in order to always apply the same action. Sure, but that would not give it any additional information in that state ST. Or the agent can pick to maybe take some form of a random action to get some new information about the environment to learn something more useful about this XSD. Because we have an unknown transition dynamics, what we're going to do is we're going to use a stochastic policy. So as we used the old notation before, we're going to say now that the action AT is conditioned on the state ST. And that is coming from some distribution pi, which is conditioned on ST. So again, this is a probability density, which gives you a density over actions conditioned on this state. And now the goal of the agent is to find the best pi such that it maximizes its performance. So again, because we have an unknown transition dynamics, now we require to have a stochastic policy that allows this agent to explore new things around that state in order to learn. More and more useful information is needed. So now, all good. We know what we have, what we mean by a state space, an action space, a transition model, a reward function, and now we understand what we mean by a policy. So now let's think a little bit about the dynamics of this reinforcement learning agent, right? So let's think about the dynamics of this repetition that we described before. So as you recall, we had an agent, we had an environment, the agent talks to the environment responds, right? And this process repeats over and over again. So we're going to assume that it repeats not forever. We're going to just assume that it repeats for some horizon big T, right? So I'm going to execute this in a loop for some T steps. So now as the agent interacts with this environment, what happens is that it will collect some form of a trajectory in that environment. So for example, it will start at some state S0, which comes maybe given to us or some distribution or whatever. Given this as 0, the agent is going to use the policy pi that we have here in order to get an action, in order to get an action A0. So that's A0. And then this will take me to some new state S1, where that S1, as you recall, is coming from the transition model S0, A0, right? So I start from some state S0, the car is here. I apply an action according to my function rule of policy pi. So it says go forward. Given that I am in a state S0 and I apply go forward, I will observe a new state S1, which is maybe like 10 meters or a couple of meters to the front. And that, as we said, comes from a stochastic transition. So that's why we say that S1 is sampled from P conditioned on S0 and A0. Given that we are at S1, this process then repeats. I query the policy again, but giving it now S1 as my input state. And then that will give me some action A1. Then I will go to S2, right? So that gives me S1 and so on up to reaching some horizon ST. So this process repeats over and over and over again. By asking the policy what action I should take, the policy responds by an action. I put that action and that state to my stochastic transition model. It takes me to a no successor state, and then this process repeats over and over again. We're going to call S0, A0, S1, A1, and so forth, right? We're going to call that as a trajectory tau. So we're going to define a trajectory tau, and that trajectory tau is going to simply be a collection of this S0, A0, S1, A1, dot, 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 up to ST, right? So as the agent interacted with the environment responded by some successor states and also some rewards, which we will come to in a second. And then we're going to collect all these SA, 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 and so forth, and put them inside a trajectory, which we will call tau. Now, please notice that this trajectory itself is random, right? The thing is that because we have a random policy and a random transition, if I had started at S0 again, I would have drifted off in a completely different trajectory depending on the actions and transitions that I have sampled. So in other words, this trajectory tau is not deterministic. It is a stochastic vector depending on the actions you've taken and the transition models you've taken. So for example, if you had started from this as 0 by applying some form of samples, you might have drifted to this trace trajectory, or you might have drifted to this trajectory or trace, or you might have drifted to this trajectory or trace, and so forth. And that's why we cannot deal with this trajectory tau as a deterministic entity, but we need to deal with it as a stochastic entity for the reason that the transition model, as we agreed, is stochastic, and the policy itself is stochastic. So with that in mind, we know that tau is a random variable. If it is a random variable, then I can define some form of a density over that trajectory tau. So now I can ask the question of what is P of tau, right? Because we said that tau is a stochastic entity, so it is a stochastic vector, right? So now we can ask the question of, okay, if this is stochastic because the transition is stochastic and the policy is stochastic, what is P of tau? What is the density over that stochastic entity P of tau? Okay, to understand this, we know that P of tau is simply P of this following joint distribution of S0, A0, S1, A1, up to ST, really, right? So what I mean by this is that the density over this random vector tau is nothing but the density over this intersection of random variables S0, A0, S1, A1, and ST. Each of which, by the way, is a random variable in its own right, because A0 is coming from some, or AT in general, is coming from some density. ST is also coming from some density, right? Because ST is conditioned on ST minus 1 and AT minus 1. And we also will assume that S0 is just coming from some initial distribution. Right, so now we have the question to answer, and that is, what is P of tau, really? Because we want to understand how would this density look like for this P of tau. All right, so now we can try to factorize somehow this joint density, right, depending on some notion of density equations, right? And this notion is really very simple. The idea is we can, in fact, use some form of bias rule in order to try to factorize this P of S0, A0, S1, A1 up to ST. So the question is now, so here's the question we want to try to answer. how to factorize P of tau, right? So we want to understand how we're going to factorize this P of tau. Right, so let's recap. We said that in RL, we had a state space, an action space, a reward function, a stochastic transition model due to sensory noise, and then we introduced as well a stochastic policy pi. Due to that, every time the agent interacts with the environment, what it will observe is some form of a trajectory tau, but that trajectory tau itself is random because the transition is random and the policy is random. Because it is random, now we can define some form of a density over that trajectory tau, which is nothing but the density over these joint random variables here, S0, A0, S1, A1 up to ST. And the question we want to try to ask now is, how are we going to factorize this P of t? Once we understand how we can factorize this P of t, then this problem of stochasticity becomes a little bit more intuitive. So that's what we're going to do next. Right, so now we want to try to understand how are we going to try to factorize this P of tau, this density over a trajectory that the agent exhibits, which is, as we said, P of S0, A0, S1 up to ST. Okay, so in order to factorize this, we have to understand a very simple concept from probability, which is the chain rule. The chain rule says that if you have two random events, A and B, so say you have two random events, A and B, right? When you are interested in writing the joint of P of A and B, right, or intersection B, we can write this as P of B given A times P of A. So the joint distribution over A and B can be written as the product of the conditional distribution of B given A times P of A. Now it's easy to prove this, really. I mean, you can just use um, bias rule in order to prove this, but we're just going to take it for granted. And the details of how you get this can be found in the other lecture of probabilities. But now we can, in fact, extend this to more than two events by saying that if we have a set of events A1 up to AN, the joint of A1 up to AN can be written as the conditional of AN on AN minus 1 up to A1. So condition the last on everything else times the joint of everything else. So AN minus 1 up to A1. So if you do like an induction proof, you can show that using this formula, you can in fact prove that the joint density over n events can be factorized as the density over the last event conditioned on everything else times the joint of everything else. Now, please notice that you can in fact repeat this idea on this remainder here, right? So we can still factorize this guy into P of the last, which is AN minus 1, conditioned on AN minus 2 up to A1, times the joint of AN minus 2 up to A1, which is the remainder. And this process can repeat. You can go back up to A1. So now, this is a very simple idea called the chain rule, where we can condition the last on everything else, then multiply by the joint of everything else. Let's take that idea and apply it to our problem here. So we're going to write P of tau is equal to. So the last event for us, which is an here, is going to be s big T for us. So then we're going to say, okay, we're going to say P of s big T conditioned on everything else, which is st minus 1, at minus 1, dot, 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 up to s0, times the joint, which is P of st minus 1, at minus 1, up to s0. Good. So we just simply applied the chain rule from here, right, from this equation to this equation. So we said we're going to have st conditioned on everything else, analogously an conditioned on everything else, times the product or times the joint of the remaining events, which is in this case is st minus 1, at minus 1, up to s0. Analogously here, the other remaining events are an minus 1 up to a1. Now we're going to use an assumption embedded in the name of a Markov decision process. Markovian assumption says that the future only depends on the present, irrespective of the history. So what I really mean by that is that ST itself, it only depends on the previous time step event, independent of the other history. This is what the Markovian assumption really says. It's what it dictates. It says that the event now, which is ST, is only dependent on the last step event, irrespective of the history. I don't care the path where you came from, but if you give me what is now, which is ST minus 1, AT minus 1, I can tell you what happens at S big T. So that's kind of the Markovian assumption. So invoking that assumption, we can rewrite this. So from here to here, we invoked the Markov assumption. We can write this as now P of ST conditioned on ST minus 1 and AT minus 1 times the P of the remainder, which is AT minus 1, ST minus 1, up to S0. So notice here I just flipped these ST minus 1 and AT minus 1. So it used to be ST minus 1, AT minus 1. I just made it AT minus 1, ST minus 1, which is the same thing. So now it's interesting to realize that this here, right, this thing here is something we defined before, right? This is something we know. That is nothing but the transition model, right? So it is this form of a model where you give it your ST minus 1, your like previous state, previous action, right? And then it gives you your successor state. So that's interesting because it seems we are on the right track because we're already observing components of the problem, of the MDP problem definition inside the trajectory, which is something that really should happen. And now what we're going to do is simply we're going to apply this idea of chain rule again, but for this entity here. So we're going to say that PAT joint of AT minus 1, ST minus 1 up to S0 is going to be again factorized into, so this can be again factorized into P of AT minus 1 conditioned on ST minus 1 up to S0, right? So everything else, times the joint of everything else, right? So all I did here is I applied the chain rule once again. So I said, okay, now I have AN minus 1 up to A1, which is AT minus 1 up to S0. And that can be, using the chain rule, further decomposed, further factorized into AN minus 1 conditioned on AN minus 2 up to A1, times the joint of the remaining AN minus 2, AN minus 1. So I can factorize this into at minus 1 conditioned on st minus 1 up to s0, multiplied by the joint of the remainder. But now it's also interesting to realize that this itself, this guy here, right, is nothing but our policy. Because it is some rule that given your at minus 1, your st minus 1, it should give you some at minus 1. Again, because of the assumption that we have a Markovian process, it suffices to have a Markovian policy, which means that we can, in fact, get rid of all this history according to the definition of our policy, if you recall, and just say that this is P of at minus 1 given st minus 1. So now that's interesting because we have the equation that looks like this. So you have st given st minus 1, at minus 1, which is your transition model. Then you have the density of picking your action, at minus 1, given that you were at your state st minus 1, which is your policy. And then you have this p st minus 1 up to s0, right? So then you have p of st minus 1 up to s0. Well, now, by now, you know what's coming. So now you can just simply apply this chain rule over and over and over again until you go back to S0, right? So you can say, I have now st minus 1 conditioned on st minus 2, at minus 2, times at minus 2 given st minus 2, times dot, 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 up to the first S0. So what you can do now is you can write this as st given st minus 1, at minus 1. Then you have p of at minus 1 given st minus 1. Then you have p of st minus 1 given st minus 2, at minus 2, times p of at minus 2 given st minus 2, dot, 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 until you get back to p of s0. So just one word on P of S0. What I introduced here is an initial state distribution. So I said that the initial state is sampled from some distribution. I mean, that can be deterministic, but I just assumed that there's some form of a given Gaussian, which gives me S0. So in GEM, if you do n dot reset, that's what this is supposed to be doing. But now I can just write this a little bit cleaner, where I can say, okay, this is nothing but P of S0 times the product over time of P of ST given, this should be, right, so this should be ST plus 1 given ST and AT times the policy pi, or the P of A given S, which we just call pi. It's just the notation we used. I mean, you can write this as P of actions, but yeah, AT given ST. So now we were able to factorize the P of tau into this equation. So what I've done from here to here is I've simply just rewritten this in a more concise form, right? So I took P of S0, right? I put it there because it's not conditioned on anything else. And as you see here, we always have this product of ST given ST minus 1, AT minus 1, and AT minus 1 given ST minus 1. So then I just put them there, and then I had a product over time, which yields back this equation. So now we were able to factorize the density over the trajectory tau into this form. And now it's interesting to understand this form intuitively, because this is a very intuitive equation. So what this is saying is that, imagine you have like this space here, right? So like a space of states cross actions cross time. Or no, without cross time, because that would be a point, but just space of states cross actions. What this guy is saying is that the first thing the agent will do is it will start from some S0 coming from P of S0. Then it will take an action A0, right? And then that will take me to S1, and so on up to ST. The density of this trajectory is simply the density of starting at S0, picking the action on that state, then transitioning according to your transition model. So the way the density of the trajectory works is really intuitive, because you start at some place, you pick an action according to some distribution that takes you to another place, and that's what's reflected by this product. So you start at some place, then you pick the action according to your policy that it takes you to your successor state, ST plus 1, given ST and AT, dependent on this product over time itself. So now that we have understood how to factorize the trajectory in a reinforcement learning problem, next what we're going to do is we're going to finalize this lecture by defining the optimization problem we would need in reinforcement learning. So what is the agent going to be looking for? Right, so we so far have shown that P of tau, right, can be written as P of S0 times this product over time of P of ST plus 1 given ST AT times the policy of applying AT in ST. So now we understand that. And then we need to think of some notion of measure that will allow the agent to learn a good action selection rule pi, right? So remember in the previous slide, we said that our goal is to find the best policy. And now we need to understand, what do we mean by best? Okay. In order to understand that, we're going to now think a little bit more about the reward that we get over a trajectory tau. So remember that, we had this interaction of the agent and the environment. And we said that the agent takes an action. The environment gives me a state and a reward. So far we have handled these two components, the action and the state, but we didn't talk about the reward yet. Well, what we're going to say is that for every trajectory tau, we have a reward, which we're going to call R total of tau. So the idea is that for every transition that you would get, state and action, you will get a reward value corresponding to that state and action. So as you recall, we defined the reward function R to be from S cross A to real numbers, which means that at every state action pair STAT, this reward, right, is gonna get for us a specific value. So therefore, what we're gonna do now is we're gonna say that we have a function of these transitions in the trajectory SA, SA, SA. We're gonna sum them up, and that reward of STAT, it's over sum over time, is going to be the total reward of that trajectory. So how good a trajectory is that the agent has taken is simply going to be the sum of the instantaneous rewards that the agent has achieved throughout its interactions with the environment. So for instance, let's say this is the goal, right? And this is the starting state. This reward, this trajectory will have a higher reward than a trajectory that looks like this, for example. Why? Because, well, it has achieved the goal, and the way we coded this reward function is that it gives me higher numbers if I achieve the goal. Now, by no means this reward is dense, and this reward can actually be very sparse, and that's what makes the reinforcement learning problem really difficult, if the reward itself is extremely sparse. So if the reward function was not like some form of a distance of approaching a certain goal, but was more like 0 and 1, where 0 if you didn't reach the goal and 1 if you reach the goal, then you can see that the numbers you would get for different trajectories that have not achieved the goal are going to be zeros, which means that that's not much information. And that's why it's hard to learn in reinforcement learning. But all these details we will come to later. But for now, we're just trying to do the problem definition. So please understand that now the reward of the trajectory is nothing but the sum of instantaneous rewards that you get along that trajectory. And please remember, right, that the trajectory itself is random vector because that's why we had to define a density for that trajectory P of tau. Consequently now, if we are to measure the performance across tau, we need to handle that in some sort of a stochastic manner. We cannot say, just give me R total tau to be maximized for one tau. Either you have to do it over all tau, so for every tau you want that to be maximized, but that's a very, very hard problem definition because you will have infinite number of possibilities. Or you can say, on average, I want a policy that gives me a big R total. So what I want to say is that I want a policy pi, that gives maximum R total on average over trajectories. Tau. So this is an intuitive explanation, right? So we want to have a policy pi that gives me the maximum reward on average over trajectories tau. So now what does on average mean, right? So what does on average mean? Well, mathematically on average means expectation. So you want to have a policy. So we want a policy. We want a policy that does well in expectation over trajectories tau. So in other words, we want to maximize with respect to the policy pi, because we want a policy that does well, which means it gets the maximum R total on average, which is an expectation of the reward R total over tau. So now what we want is we want to get a maximum reward total on average, and we want to find that policy pi that will give me that best performing reward total of these trajectories. Now, if you remember the definition of expectation, right? So if you had some random variable x, and now you try to do e of a function of x, that is the integral, right, if x is continuous, of p of x, f of x, dx, right? So if you want to try to find the expectation of some function of a random variable x, that is nothing but the integral over the distribution over, or the density of p of x times f of x dx. So if it was discrete, you would have a summation p of x f of x dx. In continuous, it's just the integral p of x f of x dx. So when I write x is sampled from p of x, so e of x sampled from p of x of f of x, I mean nothing but this definition. So I mean that this is e over f of x, where x is a random variable coming from p of x, is nothing but the integral of p of x f of x dx. So to take this notation to our scenario here, tau is our random vector, right? And now what we're going to say is we're going to say that we want to maximize E over tau because it's our random vector. But tau is sampled from what? Well, it's sampled from the density over trajectories, which we just derived. So that is P of tau, R of tau. And of course, some people would like to put P pi here because that depends on pi. That's what the agent can control. Of course, it's pi and transition, but transition we cannot control. So that's why we just put P of pi. And I can therefore write this as max expectation over trajectory sampled from P pi of tau of R total. So what this equation is trying to say, give me the best policy that on average over trajectories tries to maximize the total reward of these trajectories. And that is the definition of a reinforcement learning problem. And that is you want to try to maximize the total reward on average over trajectories. As we said, please notice the definition here. So as we said, like just to be clear, max over pi, E over tau sampled from P pi is the same as saying that's the integral over P pi of tau, R total, of tau d tau. So there's a density for the trajectory, and that density is multiplied by the function d tau. So in other words, integral of p of x f of x was the expectation over x sampled from p of x of f of x. Similarly here, we can say e of tau sampled from p pi tau of r total is nothing but the integral over p pi tau r total d tau. So that is the definition of the reinforcement learning problem. And in the coming lectures, we're going to dig deeper into how we solve this problem. And the current literature in RL is really trying to handle this problem, but in different ways. So we're going to talk about some approaches to solve this problem. And of course, the later lectures will be a little bit more practical, where we will implement some of these solutions in OpenAI Gym. But this lecture set forward the problem definition of reinforcement learning. And I hope it's clear enough to understand why this method is cool, because it covers a broad range of applications, and how we achieved this problem definition, starting from the definition of the MDP to the definition of the stochastic policy and the stochastic transitions, to understanding the density of P pi of tau, to getting our final problem definition. Right, so to summarize, we know that now reinforcement learning covers a broad spectrum of applications, such as robotics, logistics, computer games, finance, and so on. We know that agents interact with stochastic environments, and the problem is described as an MDP, or a Markov Decision Process. And that is represented by a state space, action space, reward function transition model. The transition model itself is stochastic. The action space dictates the type of policy you will use, which is also stochastic. And the goal of an RL agent is to find the sequence of actions, which is represented by the policy, to maximize the total return on average over all trajectories. And mathematically, that meant to us that we want to maximize over the policies, the expectation over the trajectories sampled from the policy, from the density, which depends on the policy of R total of tau. So this is our goal, and that's what we want to try to talk about in the next lecture. How are we going to be able to solve this type of problem? And we're going to categorize different reinforcement learning solutions. So maybe until then, it's worth thinking, how would you approach solving this problem? Right. So thank you for following us in this lecture from the Machine Learning and AI Academy, where we hope that you will have the ability to grow your future with artificial intelligence. So we're now just discussing reinforcement learning, specifically deep RL, and we're going to detail some of the applications as well as the implementations of that. But in the future, we are also planning to include different topics of machine learning algorithms, such as deep learning, deep networks, GANs, probabilistic models, Gaussian processes, normalizing flows, among others. So if you found this lecture to be interesting, and if this channel is something useful for to help you grow your future in AI, please do subscribe. See you soon.